Hello and welcome everyone. So this video is the initiation of assignment 1, CFD modeling flow about NACA 12 aerofoil. So the first thing that we all need to do is generate an Excel sheet, and this Excel sheet will help us populate and visualize what's happening in terms of the experimental results. So let's talk a little bit about this Excel sheet. Again, it doesn't need to be in the same format, but keeping it nice and simple. Again, it can be extracted and put into your assignment. So we have this section here where we've got some known measured data from the assignment that we provided. So we know what the chord length is. It's 152.4 millimeters or 0.1524 meters. The depth, 0.45 meters or 450 millimeters. The velocity, 30 meters per second. Temperature being 19. Pressure millimeters of mercury, 758.6. Viscosity, 1.46 e to the power minus 5. And the gas constant. So using these values, we can calculate the area. So the area, you can see here, everything in yellow is being calculated. And we use Excel to do our calculations for us. So again, if you haven't used Excel to calculate stuff, this is a good time to start learning how to use Excel. It becomes very, very beneficial in the long run. So the area is very simple. You can see the equation. It's basically your chord times the depth. So B3 times B4 will give us our area. Temperature is simply your B6 plus 273 to get it into kelvins. Density, as said before, so it's simply the equation where we take our millimeters of mercury, B7 divided by 760 times by 101.325, and then we divide it by our B9, which is the gas constant, times B11, which is the temperature in kelvins, and that provides us our density. The Reynolds number for the chord, again, B12. So here we're taking the density times the velocity times the chord length, which is this one here, divided by mu, which is our viscosity, and that provides us our Reynolds number. So here, again, I'm not looking for all of this in the assignment. I am looking for hand calculations of each section. So with that information, we can then, from the assignment, we know what the angles are, 0, 2, 4, 6, 8, all the way to 20. And then we've got some experimental values. So the table in the assignment brief provides our lift and drag. And these are experimental, so they are from the WGU wind tunnel results that I've conducted a few years ago. So we've got our lift values going from 0 to 20 and our drag values going from 0 to 20. And it's very important that we have a section here where it's got CFD results of lift and drag, and then it's got CFD results of lift and drag as well again. And you may say, why is there two? Now, because this is a two-dimensional simulation, ANSYS Fluent will by default take the depth as 1. So Z becomes 1. But we know that there is a depth of 0.45. So therefore, the results that come from ANSYS, we put them in here, and then we multiply them by 0.45. So you can see in this section here, it's F3 times 0.45 to give us our actual CFD lift result, which is multiplied by 0.45 meters. Same with the drag. And then once we've done that, we can then use the equation 1 and equation 2 to calculate our coefficient of lift and coefficient of drag. So these are all in newtons, and the coefficient non-dimensionalizes them, and we always represent aerodynamic characteristics in coefficients to give us a better understanding. So here we've got the experimental values, and you can see the equation here is very simple for CL. So it's lift divided by half times the density times the velocity squared times the area. So here D3, which is basically the lift here, divided by 0.5 times our density, which is provided here, squared times our velocity times our area. And you can see that I've got these dollar signs. What the dollar sign does in Excel, it means that these are actually locked. So when I drag these down, it won't change by these, because usually when you drag these down, it drags down whatever column you selected on the other end. For example, F3 for in this case will drag down as long as I drag this down as well. But however here it locks them into place so they won't change. And exactly the same I've done for the ANSYS numerical values here as well. And I've already pre-populated some tables and graphs here so we can see the experimental values as well as our numerical values. And for this instant, I'm only going to simulate 4 angles so we can quickly see what they look like in terms of are they very similar or close to the experiment. So the next thing that we need to do is take the coordinate files from the assignment brief and generate a new Excel file, which then we will convert into a code that ANSYS can read in order to generate the numerical modeling. So what I will do now is open up a new Excel, and with that Excel sheet, what we want to do is at the first top is provide some values. Now it's very important that ANSYS reads this code correctly. So in C1 here, what we want to do is give it a code. So that's hashtag NACA 0012. And then on the first one here, it's going to be hashtag group. The second one's going to be hashtag point. Then we're going to give it the X, Y, and Z coordinates. So here, X underscore chord, Y underscore chord, and also Z underscore chord. So we know these coordinate files that have been provided from the assignment. So what we can do is, if you have the assignment open, you got the X chord and the Y chord, you can just copy these. So right click copy, or Control C on the keyboard and Control V, and it will paste them in there. All we want to do is later on we'll tidy it up because we don't need the borders or anything. So once we got that, we just need to take the lower coordinate file, Control C, and then go down here and paste them here. So we've got our coordinates now. We've got the upper coordinates and the lower coordinates. So it's very important that we say that the upper coordinates belong to group 1. So 1, 1, highlight these, bring them down to here. So that's group 1, and then 1, 2, 3. How many points are in group 1? So we take them down there, and there's 34 points. We can copy that, Control C, and paste it down here because they'll be exactly the same. And then these belong to group 2. So group 2. So we've got all of those in place. Now the Z coordinate, because it's a 2-dimensional simulation, we want to put 0. And you can just simply double click on this and it will populate everything that's on the left hand column to 0. And here now we just highlight all of them, no borders, and we have everything ready to move to ANSYS now. So obviously here, file, save as, make a working directory wherever you need to. So I'll make a new folder, ANSYS, and in here NACA 0012. Save. Okay, why is that not saving? Okay, give it another name, AA. Okay, and now to generate the code, file, save as, browse, and we save it as text tab delimited. Very important that is this file here, text tab delimited. So select that, save, it'll come up with a message, press yes, and now in that folder where you've created it, documents, ANSYS, you'll find your Excel file and then your NACA text file. And this is the file that we need in order to generate our model in ANSYS. So now that we have the Excel file ready with all of our calculations and we've got our NACA profile code generated, we can go straight to ANSYS in order to run our model. Now, obviously, opening up ANSYS, I've already got one pre-opened. Don't know why I've opened another one. Just close that. Okay. So again, make sure you got it in the right working directory and saved it. So files, save as, documents, wherever you want to have it, ANSYS, and this is 001, assignment 1, and it's nice and saved. Okay, so grab a full system analysis. We don't need to grab any individual components. So fluid flow fluent, right click on geometry, new design modeler, give it a few seconds. You can see it down here, it's starting. And obviously here the units needs to be in millimeters, as we're going to work in millimeters. And the first thing that we need to do is obviously just select your XY plane, look at, we can see what's happening here, so it's in the XY format, and I always work in this way. So X1 or positive X is the airflow, gravity working in the -Y direction, and Z looking towards you. And we won't be using Z, this is 2D. So to bring in that code, concept, 3D curve, from coordinate file, okay, make sure that's selected. Select your file, so now again go to your desktop, your documents. So documents, go to your working file folder, and you will find that text document. Open that up and then press generate. Now at first you won't be able to see anything depending on how you have it. Press the look at face plane sketch, and you can see that here the profile has been generated and it's come in as a line body. So what we want to do is go to concept, surface from edges, press the control button on the keyboard, select the upper and the lower, apply, generate, and now it becomes a surface. Now as you know, it's non-dimensionalized. The coordinate file from here to here is exactly 1 millimeter. So what we want to do is we want to scale this to 152.4 millimeters. But before we do that, it's ideal to centralize this one. So we want to make sure that when this rotates, it rotates in the middle. So from here to here is 1 millimeter. So all we need to do is move this surface 0.5 millimeter in the X direction. So body, translate, select this body, apply, double click on direction definition, -0.5, and press generate. And what it's going to do, it'll move the surface, but it'll leave the edges, and we don't need these edges anymore. So select these two and suppress the body. So again, you can either, nope, it doesn't work. So click on that. Here we have this now. So all we need to do now is scale, select this body, apply, 152.4 millimeters, generate, and now it's up to scale, and it's exactly where we need it to be. So before we start rotating and drawing everything in, we're going to just think ahead a little bit. So what we're going to do is create body, rotate, select this body, apply, double click on selection. Now you can see here it's gone the downward direction, so because x equals +1, so if we put x equals -1, it goes in the right direction, and then we can put 0 degrees here and then generate. Now I'm using this at the moment because remember that I said in the assignment brief that once the angle changes, the position of your line rakes will also change as well. So you have to do a variety of line rakes. Now for example here I might do 5 line rakes, so 1, 2, 3, 4, and then one right at the end. So what I'm going to do is I'm going to go to Tools, Analysis Tools, Entity Information, and I want to select the point tool and click on this point here, and that tells me that this is minus 76.2 millimeters. So in your Excel sheet that you've created for 0 here, just put minus 72.6 millimeters. So minus 76.2 millimeters, minus 76 millimeters. And again here, now what I'm going to do is I'm just going to rotate the angle to my next desired angle. So I might say 8 degrees, generate. And again, tools, entity information, select that point. And that's minus 75.45, minus 75.45. So, and that's for 8, minus 75.45. Change the angle again to say 14 degrees, generate, tools, analysis, entity information, make sure you've got the point tool selected. This is minus 73.93, 14 degrees, minus 73.93, and then the last but not least 20 degrees. Again here, just rotate this one to 20 degrees, generate, tools, analysis, entity information, point tool, and that's 71.65, minus 71.65. Okay, so we have that now, and we'll use that data later on in order to find out what the actual positions are for each section. So 72.6. Okay, that's good. So once we've got this, rotate. We want to put that back to 0. Generate. And once it's on 0, we're going to click this box, and this is where it becomes a parametric function. So here, put AOA, angle of attack, and that's going to be our angle. So what that means is we don't need to generate different models for different angles. We use one geometry file, and we have the angle of attack as a parametric function in order to give us all of our results. So this speeds up the whole process. So once we got that, X, Y, look at, we want to zoom out a little bit by using the mouse roller button, and what we're going to do is put a new sketch, and we're going to sketch a rectangle, which is the wind tunnel around. Anything like this would be okay. And then go to constraints, symmetry. So again, select the left axis, and then left edge, right click, select new axis, x-axis here, top edge, bottom edge, and that's now symmetrically constrained. So now we can give it a dimension, and what you'll do here, 1000 millimeters and 450 millimeters. So now we have this domain here, which is a sketch. We can go to concept, surface from, sketches, sketch 1, apply, add it as frozen, generate, and it becomes 2 separate bodies. So we've got the macro profile, and then we've got the wind tunnel. So we're going to fill this wind tunnel in with mesh, but if we mesh it over the aerofoil, then there'll be no separation of airflow. So if we subtract the aerofoil from this domain, it means that the airflow has to go around an empty void, which will then give us our characteristics. So create, Boolean, subtract, target body is the wind tunnel, and tool body is your surface body first, which is the aerofoil. Once you press generate, you'll see a hole cut out through the middle. And that's it. Simply, this is our design modeler part done, where we've created everything. One good thing here is just to give it a name, WT wind tunnel, and make sure that the fluid is as fluid solid as a fluid. Press generate for good luck. Make sure you press save. So you can either save here or you can save in the workbench. It doesn't really matter. So close design modeler, and you can press save here and it will save. Now once you've done that, double click on mesh. I would also strongly advise everybody to make sure you take regular breaks. This can be quite time consuming, so please do take breaks. Okay, so click on the Z. We've got our model here. There's no mesh applied to this, so it's best to start giving the name selections. So select the edge tool, select the left edge, press N on the keyboard, and you can call this one inlet. Select the right edge, N, outlet, top, control, bottom, two edges selected, N, wall, and again for the aerofoil, top, bottom, N, NACA 0012. And then obviously you can select the surface N and call this one air, because the main fluid is going to be air. So if you come up here, click the name selection, you can see simply what everything is. You can even press Control and select the inlet outlet wall NACA, and here is a nice image to show your selection. Please do not use the screen grab or snippet tool. Just simply right click and you can copy to clipboard, and this is a really nice way of putting in a nice high quality image into your working domain. So you can just simply now paste it and you can see it looks really good rather than using the snippet tool. So once we've done that, we then need to do the mesh. So again, what I tend to do is insert in a method, and the method that we're going to insert is going to be triangular, so using triangles. And we know that the mesh around the aerofoil needs to be very, very fine, because that's where the most influence is, where we don't really care what's happening up here, but we do care what's happening around here. So mesh, insert, make sure the edge tool selected, select the top edge, bottom edge, insert, sizing, and again here, because the units are in millimeters, it's got 54. Let's put a value of 1 for now, so a value of 1 in there. And then if we go to the mesh, open up the sizing, you've got the default 54 millimeters, so you can see that that circle there around the mouse is 54 millimeters. So let's change that 54 to say something like 10, and you'll see that that goes much smaller. So I'm going to use 25 for this one here. Let's generate the mesh, and you see something very systematic like this, which is not bad. High defined mesh around here, large mesh everywhere else, so it should give us some good results. So remember what I said about the quality. So statistics. So statistics wise, 5,920 nodes here, so that's one element that we need to record. And in the quality, we've got the mesh matrix. So aspect ratio is 2.35, so it's below 10, that's very good. And the skewness is 0.54, which is what's very good. It's supposed to be less than 1. So again, this is an appropriate mesh, but however, you could investigate it further. So now that we have the boundary conditions, we've got the mesh, we've got the edge sizing, we've got everything ready, what we want to do is go File, Close Meshing. You'll see a lightning strike, right click, Update. Now once it's been updated, you can either save it as a different file or save it as the same file. But one thing that you will find is you've got the parametric set ready, which I'll show you in a second what to do and what not to do with the parameter set. So green tick means everything's correct. If you have a X on here, it just means that you probably somehow selected something and gave it the a different name selection. So you probably selected, for example, the inlet and the outlet edge and gave it the same name. No edge can have two different names, so it has to have a single name attached to it. So again, setup, double click. Here, automatically it's selected 2D, so it knows. If you've got a powerful computer, you can run it in parallel, but as I said, if it's your own personal computer, just run it in serial. Just take a little bit longer, but 2D, 5,000 elements will be done within a few minutes. So press OK. Okay, so first things first, turn on the gravity, minus 9.81. We then go to the models, and here we want to go to viscous because we know that the turbulence model we need to select. So you've got the Spa-Almers, K epsilon, K omega. There's also the transitional K omega models, transition SST, Reynolds stress, scalable adaptive simulation, and detached eddy limit simulations. It's very important that you don't go too far down because these require a lot more longer simulation time. The detached eddy simulation could take a fair few weeks, for example, where the Spa-Almers was designed by NASA for NACA profiles. K epsilon is the most standard used turbulence model, and the K omega again is a good ideal model, and then obviously you've got the transitional K omega model. So again, up to you how you want to do this. I always start off with the K epsilon model, keep the model standard wall function, do not change anything. It can have a detrimental effect on the simulation results if you don't understand what these are, but we do go into these a lot further in the master's program if you wish to take this further later on in your academic career. So we selected the K epsilon model. It's a steady simulation, it's not time dependent. So total gravity, viscous model, K epsilon selected. Now in the materials here, air is automatically there, and this is where you can change the density and the viscosity from the experimental. So in your Excel sheet, the density is 1.2, the viscosity is a different value. You can change these here. So at the moment, I'm not going to change them. This is something that you will need to change, but remember that you need to describe in your assignment how you changed the material properties. Boundary conditions. So double click on boundary conditions. So we got our inlet. Edit this. We know that it's 30 meters per second. And again, the turbulence, we know that the hydraulic diameter is, we know the dimensions of the wind tunnel. So the hydraulic diameter here is going to be 0.45 because it's 450 millimeters by 450 millimeters. Press OK. The outlet has to be the same as the inlet because it's a square. So again, here, hydraulic diameter 0.45. And the pressure is 0. So we want to know that we don't know what the velocity of the pressure is here. We know the velocity is 30 meters per second coming in and going out. Press OK. So once we've done that, our boundary condition, so with the inlet, we've got the outlet. So another key thing here, what we need to know is obviously is the reference value. And the reference value is quite important because we're trying to extrapolate the lift and drag from the simulation. So the first simulation that we're going to do is just quickly go from here, compute from inlet, and the area is obtained from our Excel sheet. So it's 0.06858. 0.06858. The depth is 1. See, even if here you put 0.45 in the parametric output, it will still take it as 1. This is a bug in ANSYS. I'm hoping that they're going to fix it. So here, the length is 0.1524. Temperature there, velocity there, everything else is set up, that's fine. So in here now, we can then go to the initialization. There's two types, hybrid and standard. Hybrid is very good if you have multiple inlets and multiple outlets, but the standard is the best for one inlet and one outlet. So compute from inlet, it'll populate our velocity and our turbulent kinetic energies, initialize, and then run calculation. And as I said in a few of my tutorials and setups, provide a value of 1,000 first. If it doesn't finish in 1,000, you can run it for another 1,000, but observe the iteration graph. If the graph is plateauing, then it means it will never converge, but we are looking for convergence here. So calculate, and as you'll see, it is going in a downward motion, meaning that it's going to converge. And as you can see here, this is what we want, conversion, solutions converge. So that's very good. So that means the simulation is finished, and now we can take our results. So what results are we going to take? So we can go to the graphics, go to contours. Now here we've got static pressure. So if I press display, here shows the static pressure. And again, here image wise, just right click, save picture, or there is oh no, they've reduced it. So create. You can save the picture here this way, but there is another method. Oh, it's a Control C. So I guess there was a copy to clipboard approach in the previous versions of the software, but again here it doesn't really matter. You can just save picture, and that's just the best way of displaying it. Now sometimes it's hard to get you can zoom in, and it's hard to get the other angles exactly the same, so sometimes you can always create a view. So if you go to views options here, for example, here I move this round and I have it something like this, and that's the view that I want for all my simulation results. So I can actually give this a view, so post-processing view, save, and now no matter what I do, I can go to PP, apply, and it'll always come back to that view. So that's just a bit of a hint. So static pressure, the assignment says static pressure, velocity profiles, static pressure profiles, and velocity vectors. So this is the contour of static pressure. You can go back here and change that to velocity, show the velocity magnitude as well. You can go to the view, zoom in a little bit more to show the velocity magnitude, what's happening. Now remember the values that we've used to create the line rates, and it's very important that we take those values in a second. But I'm just going to show you the static pressure profile. Remember, the profile is what's happening on the edge. So here you've got the XY plot, plots. You got XY plot. I can click on this. Now x equals 1, static pressure Y. Select the NACA aerofoil, save and plot, and here is now my static pressure profile happening on my aerofoil, and I can actually go to the axis, not the axis, sorry, the curves, put 0 as 0, pattern line, get rid of the points, apply, close, save and plot, and it creates it into a line. Now how do you take this into Excel? You can write to file, order the points, click right, go to your working directory, documents, go to your folder and give it a name. So XY 0, for example, angle of attack, press OK. That creates a XY plot file, so you got it here. Now if you move that, just say for example there, and I open up a blank, any Excel, doesn't really matter, I can drag and drop that anywhere, click on the Excel, it'll say yes, and then what would happen is it will generate an XY file for you. So you have the XY coordinates, and you can actually go to insert a line, and you've got it there. So that's just a very simple way of extrapolating the XY data files. Okay, so close that, no, don't change. And let's go back to Altus Fluent. So I've showed you how to do a contour of static pressure, a contour of velocity magnitude, and these static pressure profiles. The one thing that we are missing is the velocity profile and the velocity vectors. Now this is where your points that we created before will become very, very useful. So we know that the NACA profile, let's have a look at the contour, so display. So we know that the NACA profile for 0, 0 is in the middle, and then it's minus 70 something millimeters this way, and positive 70 millimeters something this way. So let's go back to the Excel sheet. So this is it here, and what we want to do is just quickly just convert these into meters. So equals that divided by 1,000. Okay, so now we have these in meters. Now we know that this is position 1. So if I do here equals that divided by 2, okay, this position is 0. then this position will be that times -1. And this one will be that times -1. So, no, not that. Okay, so this is my first position, position 1, position 2, position 3, position 4, and position 5. Now, that's hard to understand at the moment, but I'll show you exactly what I'm doing now here. So, go back to domain, create line rake. Now, the line rake here, we know that in the Y position, it's if you go to your general up here, scale, it's -0.025 plus 0.025. So here, -0.025, sorry, and plus 0.0225. Okay, now the first position, remember position 1 that we've said was -0.0726. So -0.0726, and that has to be the same in this position as well. So Control C, paste, and this is P1, position 1. Create. Position 2 is -0.036. So what you can do quickly, rather than rewriting it again, we know that this is P5. Create. Then we know that it's Control C, Control V, Control V. This is P2. And then to get rid of the minus, get rid of the minus. And this is position 4, create, and 0, 0 is position 3, P3. Now, what have I done? I'll just quickly show you now. So when I go to my mesh here, I can select my NACA 12, P1, P2, P3, P4, P5 display, and you can see here that here is my NACA 12, and here you can see that the lines that I've created. Now here, I could have gone with the lines, line rake, just deleted the thing. Sometimes there's no point taking the line in the Y direction all the way up, because if you take it all the way up, it can cause some issues slightly, because it picks up the velocity at different positions. So here now, I can go to vectors. I can select P1 to P5, arrows, filled arrows, save and display, and now you can see it's showing you the velocity vectors. And again, if the lines are a little bit longer and in the right position, I don't know, for some reason my one's not in the right position, but you can fix that on yours. It shows you the vectors, and if it's a bit too much, you can always skip it by 1, and it just basically reduces the line. So that's showing the velocity vectors. Draw the mesh, show the NACA profile, display, close, save and display, so you can see the NACA profile as well as the velocity vectors. And I would make these lines a little bit longer when creating. I don't know why it's done that. Just double check. General scale. I might have put minus 0.225 minus, sorry, positive 0.225. Let's just do another one. So we got minus 0.0726 minus 0.0726 minus 0.0726. Create, close, go to the vectors, and it will just be line 11. So yeah, you can see that the line is a lot more longer on that end, and it shows you a full view of what's happened to the velocity vectors as well. So that's showing you the velocity vectors, and again what you would do is in the XY plot, because the lines are being created in the y-axis, you need to go 0, 1, velocity, magnitude, line 12 for example here, and that shows you the velocity vectors, but you would select P1 to P5, save and plot, and here you can see now the velocity profile is completely different for at different positions across the NACA aerofoil, and again you can write these to file as you go along. Now, as I said, remember when you create all your images, your post-processing images, your line rakes, it'll be only done for the 4 angles and for the best mesh and the best turbulence model. You don't need to do it for all of them, and you don't need to do it for all of your angles. So I know I kind of like jumped the gun a little bit here to show you actually how to extract the data and the results for one of the questions, but again you would only do this for the best model. But however, if you're not going to do a mesh dependency study and you're not going to do a turbulence dependency study, you can go straight away with whatever's best for you, and just so that you can complete the assignment. So let's close these. Now this is where we need to extrapolate lift and drag. So because we're going to be running a parametric study, it's best if we delete all of these, because otherwise it'll try and generate them at many times when it's running the parametric study. So delete. Okay, so we've got a blank canvas here. We go to reports, surface integrals, and not reports, forces, and when x equals 1, it equals the drag. When y equals 1, it equals the lift. So we want lift first. So select the NACA 1, make sure the wall is not selected. Now we could always print it, but that will give us the data here. But what we want to do is we want to save it as an output parameter. So here we call this one lift. And then when x equals 1, y equals 0, save output parameter, drag. Okay, so we got those. Close. File. Before we do anything else, we're just going to quickly just initialize again. Compute, inlet, initialize, yes. This time we don't calculate, we close fluent. So file close fluent. And what this does is it gets it ready to run a batch simulation using the parametric function. So here we've got the parameter set. If you click on this now, and what you'll see is you've got the angle, and then you've got lift and drag. So as I said, we'll do 0, 8 degrees, 14 degrees, and 20 degrees. What you would then do is obviously for your final model, put 0, 2, 4, 6, 8, 10, all the way to 20. It's very important here that you understand the retain function. So at the moment here, it's only retaining the simulation results for 0 degrees. So when you go from 0, 2, 4, 6, 8, 10, 12, 20, make sure you stick and you retain the images, retain the simulation results for the desired angles that you want to represent. So here, for example, I'm just going to retain these two here, just to give you an example. I'm going to show you at the moment that at the moment it's current. So once it's got that, press update all design points and give it a few minutes, and what will happen is it will pre-populate the lift and drag for you, so we can take it straight into our Excel file. So give it, and I always have a look at the show. So what it does, it's saying that it's creating the mesh, it's running the simulation, then it'll go back to Ansys Design Modeler, it will change the angle, then it'll go to meshing, it will change the mesh, then it'll run the simulation and then give you lift and drag values. So we can see here slowly we're getting some results. So what we can then do is, if we have this open a little bit, we can start populating some of these. So the lift here that we've got was minus 0.007386, and then the drag we've got is 2.6544. It's 2.6544. So that's the first result. Let's have a look. So it's down there and slightly up elevated here. Give it a few more minutes. Okay, so now that the simulation has finished for these runs, what we can start doing is pre-populating these into the results. So 8 degrees is here, so that's 57.625, and then the drag is 5.66, and then 14 degrees, we've got 82.69, and then 13.17, and then 20 degrees was 75.76 and 25.24. Okay, so having a look at the results, you can see that's very nice for the lift, but for the drag it's slightly out of balance. But in general, if these 4 results can fit really nice within the experimental value, it gives us confidence that the other angles will automatically fill in the appropriate manner. So if we now go back to ANSYS Workbench and click on Project, so currently this is only for 0 degrees. So if I now right click on the 20 degrees and set as current, now this becomes current. I can go back to Project, click on Solution. Do not click on Setup, click on Solution, and that will go straight to the results. If you click on Setup, sometimes it kind of like accidentally deletes the overall results. And what you'll find here now is that the angle now is at 20 degrees. And this is where you can, for example, go to your graphics, go to a path line, and show that stalling has taken place. So again, here I'm going to skip it by say 20, save and then here you would have to click on the default interior. So here you can clearly see that due to the nature of the angle, you can also pulse it just to show you that a vortex is generated and there's no lift. Now, if you are doing a mesh dependency study and you're not seeing any lift, any stalling, go to your contours. There should be a vortex on top. If there's not a vortex at an angle of a 20, there is a fundamental problem with your meshing, and you then either need to reduce the mesh in order to achieve this. So press stop, otherwise your graphics card could have a bit of a problem. One thing that I would like to say is that sometimes when you're running a parametric study and you have 20 different angles in here, so 0 to 20, sometimes it does get stuck. And I don't know why it does this, depending on some machines. You will find that it's just doing nothing on, say, 14 degrees. What I would do is I would go down here, press the stop button, and then restart it again. And what that will do is it will just recalculate, and sometimes it just sticks and it just moves on to the next angle and gives you the answer. If you have a persistent problem with that, then what I would then do is just run it manually. So go back, change the angle, run the simulation, and then obtain the results directly from ANSYS. So you can go to your forces, select what you need, press print, and the total value is already provided there for you. Okay. So, in a nutshell, that's everything you need to know for assignment 1. As I said, the line rakes now have changed in position. They won't be in the same position as before. So it's always important to know where the X position is for your given angles. Okay, so finding the entity information provides the best way. I just want to make sure why our one was a little bit different. I just want to double check to make sure that we use the right function. So this should be at 20 degrees. Units, tools, analysis, entity information, point. Now, so 71.605, I'm not sure why at 0 degrees that was out of balance. 6.5, yeah. 72.6. So I'm just going to go to rotate, get rid of that, put it back to 0. generate tools, entity information. My bad. That's supposed to be 76.2. There we go. And therefore that will be 76.2 there as well. Okay. All right, everyone. Hope you enjoyed it. Best of luck. And you know where I am. Need anything, just drop me a message or ping me a message on Microsoft Teams. Thank you.